right, lesson 3.3 is exponential functions. And so our skills and learning objectives here, we're going to investigate the basic behaviors of exponential functions and their graphs, and we're going to analyze exponential graphs for key characteristics such as domain, range, in behavior, continuity, symmetry, asymptotes, increase, and decrease. All right, so while exploring linear growth, we observed a constant rate of change. For example, in the equation f of x equals 2x plus 3, the slope tells us the output will increase by 2 each time the input increases by 1. In this lesson, we will explore what it means to grow exponentially. We'll look at real-world scenarios that have a percentage change per unit of time rather than a constant linear change. So the definition of an exponential function is that an exponential function in x is a function that can be written in the form of f of x equals a times b to the x, where b is a positive real integer, which means it's greater than 0, but not equal to 1, and our a cannot equal 0 and is a real number. The domain of f is a set of all real numbers. The base b is the growth factor, and the constant a is the initial value of f, which means that when you plug in f of 0, and you get a times b to the 0, which just gives us a, because remember, anything to the 0 power is 1. So some characteristics of exponential functions. If our a and b are both greater than 1, then the exponential function will demonstrate exponential growth. It's going to increase as we go to the right. If a is greater than 0, but my base is between 0 and 1, the exponential function will demonstrate exponential decay, which means it'll be decreasing as we go towards the right. So example 1 here wants the graph y equals 2 to the x. And so I'm going to start on the positive side of this. So, well, actually, I'll just start here. It says we want to just plug in what is 2 to the x when x is negative 2. So this is just 2 to the negative 2. Then we have 2 to the negative 1, 2 to the 0, 2 to the 1, 2 to the 2, and then 2 to the 3. And then it wants to know what is that y value. So what do we get? What is 2 to the negative 2? Well, don't forget, when you have that negative exponent, remember it's on top, so you're going to send it to the bottom. Now you have a fraction. So you have 2 to the positive 2 on bottom, and you don't have anything left on top, so we put a 1 there. And then we can work that out as it is 1/4. And so 2 to the negative 1, same thing. That 2 to the negative 1 goes to the bottom. It becomes a positive 1 when it gets on bottom. Nothing left to put on top. So we put a 1 up there. And so I get 1/2. And I'm sorry I missed it. I was thinking ahead here. I wrote that one was 1/4, and then I put 1/2 when I wrote it. All right, so 2 to the negative 1 is 1/2. 2 to the 0, remember, anytime the exponent is 0, the answer is 1. 2 to the first is 2. 2 squared is 4, and 2 cubed is 8. And so let's go ahead and let's graph these points. And so remember, exponential functions will have that asymptote down here. So they have a horizontal asymptote. And it's at y equals 0. All right, so look at your domain. Our graph keeps going to the left. It keeps going to the right. So our domain is -infinity to infinity. Our range, our graph does not keep going down. It goes towards the 0, but there's that asymptote there, so it's not going to touch it. So it goes from 0, and it does keep going up all the way to positive infinity. Then, as x goes to positive infinity, what is happening to f of x? So as our x goes to the right towards positive infinity here, what's happening to these y values? They're going up as well. They're going up to infinity. I'm going to back up that for a second so I can get rid of that line I just drew in. All right, so we got infinity there. Then as x goes towards negative infinity, this direction, what's happening to those y values? They're going towards that horizontal asymptote, which is at 0. All right, we said we had a horizontal asymptote at y equals 0. Intercepts, I don't have an x-intercept because that's that asymptote, but I do have a y-intercept. Is it 0, 1. And then concavity. This graph is increasing at an increasing rate. As we go to the right, it's increasing faster and faster every time we move more to the right, which means that this graph is concave up. All right, example 2. So which of the following are exponential functions? Explain why or why not. So if we look at A, we have initial value, which is 1, because remember they said that it's the initial value times b to the x. So y equals a times b to the x, where a is our initial value, b is our base, and then it's raised to the x. So because this is just 2 to the x, that's the same thing as saying 1 times 2 to the x. So our initial value is 1, our base is 2, and is this exponential? Yes, it's in the form of y equals a times b to the x. Now b, notice we have initial value, there are 4. Our base this time is x. So is that an exponential function? No. Because x is not in the exponent, it's not going to be exponential. This is actually a rational function. All right, C. My initial value is 5. My base is e. Is this exponential? Yes. X is in the exponent, so we know it's going to be exponential. And it's because it's in the form of y equals a times b to the x. That negative is just a reflection across that y-axis, okay? It's just a transformation. It's a reflection. All right, and then D, our base is 3. I'm sorry, our initial value is 3. Our base is 4. Is this exponential function? No, this is actually just a constant. It's all numbers. Remember, e is just a number, so there is no variable at all, so it's just a constant. No variables. All right, example 3. Compute the exact value without a calculator. So it tells us that A says f of x is equal to 6 times 3 to the x plus 1. And we're wanting to solve that when x is 2. So we're looking for f of 2. To 6 times 3 to the 2 plus 1. Remember, exponents first. So 2 plus 1 is 3. Then we deal with the exponential part. So 3 cubed is 27. And then 6 times 27 is 162. For B, f of x equals negative 5 times 8 raised to the x for x equals 1/3. Now remember that 8 raised to the 1/3 is the same as the cube root of 8. Okay, and we could work out that cube root of 8. If nothing else, you can use your factor tree. Remember, it's 4 and 2, so 2, 2, and 2. Cube root says I'm looking for 3 of a kind. So the cube root of 8 is just 2. I'll multiply those together, and I get negative 10. 4 says, find an equation y equals g of x that describes the function characteristics. The value of g at x equals 0 is 3. And so the output value of g doubles every 1 unit increase in the input value. So if we start at 3 and it's doubling, remember that means times 2. So that means we'd have 6, 12, 24, and then 48 here. So we want our equation. So we know our initial value. Our a is going to be 3. Our base is that rate at which it's changing. So it's going to be 2. And so our equation is just y equals a times b raised to the x. All right, example 5 says determine the formulas for the functions from values given in the table below. For each function, compute the average rate of change of y with respect to x and the ratio of consecutive outputs. All right. So look at A. All right, so looking at A there, I'm sorry, somebody came to the door. So we've got our table, and so we're looking for our equation. So we want to look where our x is 0. That's going to be our initial value. So we know that our a is 3. We can see that r, which is going to be our base, it's doubling each time, so it's going to be 2. So we get y equals 3 times 2 to the x. And because we can see here that our numbers are getting bigger, we know that this is going to represent growth. So this is going to represent exponential growth. Let me try writing that in the right order. All right, B, there's my initial value. So I know that A is going to be 5. My base, which is my rate or my ratio, I can see we're multiplying by, if nothing else, it's 10 over 20. So it's 1/2. And so my equation is going to be y equals a times our b raised to the x. And we can see in our table, we can also see though, because our rate is by 1/2, it's going to decrease, it's going to get smaller. This is exponential decay. Our example 6 says for any exponential function, f of x equals a times b to the x. For any real number x, f of x plus 1 will equal to b times f of x. And so for a, we have f of x equals 3 times 2 to the x. And it tells us if a is greater than 0 and b is greater than 1, the function is increasing, and the base b is its growth factor. So that's what we saw on that first, the example A in example 5. Sorry, in part A in example 5 was that our base was 2. It's greater than 1, which we talked about at the very beginning there when I was just going over exponential functions. So that meant it was exponential growth. So the base is its growth factor. And so we know if it's growing, it's going to be doing like this as we go from the left to the right. And so the limit as x goes towards positive infinity, it's going to go up to the right, so it's going to infinity. And the limit as x goes towards negative infinity, that's where it's getting flatter. That's where it's approaching that horizontal asymptote, which is at 0. We can see that our domain is going to keep going to the left and right. The range, it's not going to go below or even touch that horizontal asymptote. And that horizontal asymptote is as y equals 0. Then on B, our a was greater than 0, but our b was between 0 and 1, which meant the function f is decreasing, and its base b then is its decay factor. It's getting smaller, it's decaying. And so it's going down as we go from left to right. So we can see the limit as x goes towards infinity of f of x, As we go to the right there towards positive infinity, our graph is getting closer to that horizontal asymptote. And then the limit as x goes towards negative infinity. As I go to the left, my graph is going up to the left, so we're going to go up to infinity. And then for my domain, still keeps going to the left and to the right. My range, it's still not going to go down, so it's going to not touch the horizontal asymptote at 0, but get real close to it and go up to infinity. And then we still have that horizontal asymptote at y equals 0. Example 7 says big tech industries has 25 locations and is expanding by 2 new locations each year. The company growth can be represented by the function b of x equals 25 plus 10x. Central Computing, Inc. has 25 locations. And they expand by increasing their total locations by 40% each year. The growth can be represented by the function c of x equals 25 times 1 plus 0.4 raised to the x. And it wants to complete the table to show the growth of each company for the first 5 years. Well, we know in that first year that big tech is just going to, in year 0, the very beginning there, they have 25 locations. And then they're going to increase by 10 new locations each year. So 25 plus 10, plus 10, plus 10, plus 10. And then they even showed us that they got the equation then that it's the initial value, a sub 0 plus dn, right? Now, Central Computing tells us it starts out with 25. But they're increasing. It says 25 times 1 plus 0.4 raised to the x. So I could use that formula, and I didn't think about it. I could have used it on the other one. It was just easier to add 10. So for year 1 here, I've got 25 times 1 plus 0.4 is just 1.4 raised to the 1. Then 25 times 1.4 raised to the 2. Then I'd raise it to the 3 and to the 4. And then there's our equation right there that they'd given us, okay? So to the x would just be that. All right, B says compare each function on the grid provided to compare the growth of each company. So it wants us to plot these points. So let's see, for big tech, we had 0 and 25. Okay, so we plotted 0, 25, then it was 1, 35. Oops. 25 would be here. 1 and 35. 2 and 45. 3 and 55. 4 and 65. And so this would be a graph on my line there. So this is for big tech. Or, you know what, they called it B of X. All right, then we can do the same thing for the central computing. So we know at 0 was 25. 1 is 35. 2 was 49. 3 was 68.6. And 4 was 96.04. All right, B wants to state the C says to state the domain and range for B of X and C of X. So for B of X, and be careful because it is linear, but we're dealing with a real world scenario. We can't have less than year 0, right? So we know that our domain is going to go from year 0 to infinity. And its range is going to start at 25 and go up. For C of X, same thing, the domain is going to be 0 included to infinity. And again, the range is from 25 to infinity, and the 25 is included as well. D says, when do both companies have the same number of locations? So that's in year 0 and year 1. They both have 25 and then 35 locations. And then E says, what is the maximum number of locations for each company in 5 years? So B of 5 will equal, they gave us that equation, remember it was 25 plus 10x, so that would be 5, so 75 locations. And then for Central, they gave us a formula that was 25 times 1 plus 0.4 raised to the x, and our x here is going to be 5. And that's going to give us approximately 134 locations. I'm not going to use a decimal on that one. All right, and that is the end of lesson 3.